Hello everyone. So today we're going to continue our video on a discussion on 6.1. So last video we get to talk about what is chain rule. From 6.1 we have this definition right here which say that if you have a composition between F and G where F map from R to Rm and G map from Rm to R, we can form a composition H which is G composition F, and we do take the derivative of H. One way to do that is to apply chain rule, which basically requires us to form the dot product between the gradient vector and the standard tangent vector. So what I want to do today would be to start off with showing you some example on how to do this. Oops. Here we go. So let's say we have this example right here. Let's say we're given a function f that map from R to R3, where f of t is equal to t squared t to the third. Notice that f represent a curve in R3. Now let's say we also given a second function g that map from R3 to R. So let's say function g of x, y, z is equal to, let's say x cosine y plus z. So notice that in this case, g represents, a three-dimensional surface, in R4. So I won't be able to draw you what this three-dimensional surface in R4 will look like, but we can still do math with it. So let's say we go define a composition. Define h of t is equal to g of f of t. What I'm going to ask you to do is the following. So want to show you the differences between, remember, we can always form this composition one of two ways. I can keep it as a composition, or I can actually perform the composition and form a new function out of it. So I want to show you what's the difference between the two. So I'm going to ask you to do is, I'm going to ask you to go ahead and find h prime of t using the chain rule from 6.1. Okay, so how do we do that? So actually pretty simple. So in this case, according to chain rule 6.1, h prime of t would equal to gradient of g of f of t dot product f prime of t. So I just have to form these two things and then do the dot products. So let's start with g. So g of x, y, z is equal to x cosine y plus z. So therefore, what is the gradient of g of x, y, z going to be? So once again, what I'm going to ask you to do is go and pause the video and go and try to figure out what the gradient is. And then once you're done, you can unpause the video so we can continue. And of course, I'm going to continue to do this. So what is the gradient of g in this case? The gradient would actually going to be the following. So if I take the derivative with respect to x, that would be cosine y plus z. If I take the derivative with respect to y, it will be x negative x sine y plus z. If I take the derivative with respect to z, I actually get this exact same thing. So that's what gradient of g is. So now what I'm going to need to do is to basically form gradient of g of f of x, or f of t. So what is that going to be? That means basically is gradient of g of f, which in this case t squared t to the third. So therefore, meaning t squared t to the third, just basically going to x, y, and z. So therefore, it becomes cosine t squared plus t to the third, negative t sine t squared plus t to the third, negative t sine t squared plus t to the third. So that's what gradient of f is going to be. Now, next thing I need to do is find f prime of t. So let's do that next. So f of t is equal to t squared t to the third. So therefore, f prime of t should equal to 1, 2t, 3t squared. So now I'm ready to form h prime. So h prime of t is basically just a dot product between these two things. The two things that we have are this one and this one. So let's go for it. So that just means cosine t squared plus t to the third, negative t sine t squared plus t to the third, negative t sine t squared plus t to the third, dot product 1, 2t, 3t squared. So remember, dot product return a single value. So basically what you do is pair them up and multiply and then add them together. That's the important part. So therefore it becomes cosine t squared plus t to the third minus 2t squared sine t squared plus t to the third minus 3t to the third sine t squared plus t to the third. So sim to me, this is what h prime is going to be. You can probably combine the last two terms together by factor out sine t squared plus t to the third, but I'm probably not going to bother by that. So that's one way to do it, is to keep the function h as a separate two function which form a composition. And then if you keep it that way, you have to kind of use the chain rule from 6.1 to evaluate the derivative. Now, what else can I do? Well, I could actually do the following, which might wind up being easier or more difficult depending on the function that we have. In this case, I'm going to ask you to find a formula for h of t, and then find h prime of t without using the chain rule from 6.1. So once again, the idea here is that if I combine f and g together to form a new function of h, then I no longer look at them as a separate two function that composition together, but instead look at it as one single function. Then the chain rule from 6.1 does not apply anymore, because now I'm looking at it just a function that met from R1 to R1. Instead of a function that met from R1 to R, in this case 3, then R3 to R1. So let's try that. So what is h of t equal to? Well, h of t is equal to g composition f of t. That means g of f of t. That means g of t squared t to the third. And that would mean that what we have is t cosine t squared plus t to the third. So now we're going to find h prime of t. So h prime of t will be the derivative of t cosine t squared plus t to the third. That is a product between two things. Therefore, I'm going to apply product rule. It will be 1 d2 plus 2 d1. So that come out pretty simple on this side at least. The derivative of t is just equal to 1. So therefore what I have is cosine t squared plus t to the third. Notice that we have that on the other method also. And what happened to this thing right here? Well, that would be plus the derivative of cosine t squared plus t to the third, so that would be t times the derivative of that would be negative sine t squared plus t to the third. And then chain rule from BC calculus still apply, and that would require us to multiply this by the derivative of t squared plus t to the third, which is 2t plus 3t squared. So if I simply multiply t into 2t plus 3t squared, and then distribute to negative sine t squared plus t to the third, then what I have will be the following. Actually minus, I'm sorry. 2t times t is 2t squared sine t squared plus t to the third. And then t times 3t squared is 3t to the third with the negative, meaning minus 3t to the third sine t squared plus t to the third. Notice that this gives us the exact same thing. Now, this still requires chain rule, but it's a chain rule from BC calculus, which does not require the product rule, dot product between a gradient and the tangent vector. That's the difference. Okay. Now, show you another example before I talk to you about something else. And then we're going to talk about a different topic, which is the last topic in 6.1. And I know 6.1 is packed with a lot of stuff. This is the third topic in 6.1 already. So next example will be this one. Hopefully it will be straightforward. Let's say we're given a function g, which is mapped from R2 to R, with g of xy is equal to x squared y plus xy to the third. And let's define a function f that from R to R2, and that would be and let's say the function f f of t is, let's say, negative t plus 2 and t plus 3. So now, once again, you need to know this, and remember, in this case, G represents a two-dimensional surface, so I'm going to just say surface in R3, while F represent a curve in R2. Let's say I'm going to define a function capital F of t, which is equal to g of f of t. What I'm going to ask you to do is I'm going to ask you to find f prime of t using 6.1 chain rule. So meaning that I don't want you to form the function f, capital F, and then take the derivative using BC calculus derivative. I want you to use a dot product chain rule. And on your next test, some question might specify just like this. And then what I'm going to ask you to do next is, how about I ask you to evaluate this? How about I ask you to evaluate f prime at 2? After you find f prime of t. Okay? So let's go and do this. So let's try to find f prime first. So the way to do that is the following. To find f prime of t, that would basically mean gradient of g of f of t dot product f prime of t. So once again, it's just a matter of figuring out what those two things are and then do the dot product. So let's start with gradient of g. Gradient of g of xy would equal to 2xy plus y to the third, comma x squared plus 3xy squared. So if I plug in gradient g of f of t, then what I have will be the following. Will be 2 negative t plus 2 times t plus 3 plus t plus 3 to the third, negative t plus 2 square plus 3 negative t plus 2 times t plus 3 square. Now that's definitely a lot of cleaning up to do. If you want to take a minute to do that, you can. I'm going to go and let you, I would suggest that you pause the video and then try to clean it up. But I'm obviously going to continue. All right. So if you go ahead and multiply everything out, you should get this as an answer. So t to the third plus 7t squared plus 25t plus 39, and then negative 3t to the third plus 25t squared minus 67t plus 58. So hopefully I didn't do it incorrectly. And so now it's just a matter of finding f prime of t, which is actually pretty simple. F prime of t should equal to negative 1, 1. So that's easy. So therefore, what is capital F prime of t going to equal to? Basically just equal to negative t to the third plus, or actually negative t to the third minus 7t squared minus 25t minus 39 plus negative 3t to the third plus 25t squared minus 67t plus 58, because just basically the first term times negative 1 plus the second one. So it should come out to be this right here, negative 4t to the third plus 18t squared minus 93 or 92, actually 92t, and plus 19. So hopefully this is the correct answers. And so now what we're going to do is now we can evaluate f prime of 2. So f prime of 2 would be this. Would basically just be this. Oops. So let's see. Let me just type into my calculator, figure it out. Hopefully it shouldn't be too hard to do. So it looked like come out to be negative 125. So that's what the slope is. Now, and you guys know how I work. I mean, you know, now that we did all this math, you get a number, which is an answer. But like, what does that number actually mean? What does it do? What does this negative 125 actually tell us? Well, in order to understand what this number actually tell us, well, clearly, the first thing you need to understand is that this derivative is technically speaking the same derivative as the derivative you learned from last year. Why? Well, because if you think about it, in this case, our function f mapped from R to R2, and our function g mapped from R2 to R. In this case, our composition f, which is g composition f, actually mapped from R to R. So it's the same type of function from what you have learned last year. Basic calculus. Real value single variable function. And so therefore what we have here is technically speaking a slope. Just like what we learned before. But what kind of slope it is? Now, in order to understand what that is, you need to understand what we actually trying to accomplish when we form a composition. So let's think. In this scenario right here, remember our f represent a curve in R2, while g represent a function that is represent a two-dimensional surface in R3. So take a minute to understand what's going on here. Suppose I draw my usual R3 space. Here's my x, y, and z. I'm going to define g to be g of x, y equal to z. And we'll define f to be f of t equal to xy. Then what does the function f do? The function f take in t and will then use t to plug into g. And what is the output of f? Well, the output of f would be z. Okay, remember the picture where we start from t, we go through f to get to xy, and then xy then go through g to get to z. And that is, in this case, how function f would do. F directly go from t to z. So when we do this, what's actually happening? So let's try to figure this out. So let's think about what g is first. G is basically a surface in R3. So let's say here's my function g of xy equal to z, which form a two-dimensional surface. Okay? What does f do? F form a curve in R2. So instead of drawing the R2 in a different spot, notice the f map into xy, which is actually what's on the xy plane. So therefore, I'm going to go and draw my f. So f forms some kind of curve. So it doesn't really matter what the curve looks like, but I'm just like to draw a loop. So let's say this is how the curve looks like. So this curve is completely flat on the xy plane. Okay? So now what's actually happening? So here we have this curve, which is f of t equal to xy. So what's actually happening? So let's examine what happened at some particular point. Let's say at t equal to some unknown value t sub 0. What happened is f of t sub 0 will yield a position x sub 0, y sub 0 on the xy plane. So that would be this one point right here, x sub 0, y sub 0. And that's what, when you plug into the function f, you get. Now, what are we going to do with this x sub 0, y sub 0 value? Well, we're going to plug it into the function g. That's what the composition asks us to do. So when that happens, what will happen is this one point would now get translated in onto the surface into this point, x sub 0, y sub 0, g of x sub 0, y sub 0, which basically gives the z value. Now, here comes the important part. What happens if I take the point on the bottom, x sub 0, y sub 0, which is defined by t equal to t sub 0? And what happens if I change t sub 0? Well, what would happen is when you change t sub 0, this point x sub 0, y sub 0 will move along this red curve. And when it does, the point directly on top of it, x sub 0, y sub 0, g of x sub 0, y sub 0, would have to move along with it. But while it's moving, it must maintain the fact that it stays on the surface of g, because it has a specific z value that's defined by g. So therefore, what happened is it would actually trace out some kind of curve that kind of mirror what's on the bottom, but with different heights. So therefore, what is actually happening here is the following. When we form this composition f, what we essentially doing are the following two things. Number one, note that when we're doing this, we are basically, when we form this composition, f is basically function g with a restricted domain of f of t. G of xy. So essentially, the function f do what g does. Why? Because it has the same exact output, z. But what's the difference is, instead of the function g, which allow the domain to be the entire xy plane, when I form this composition, which is called capital F, I'm basically restricting the domain of g onto just this one curve, and therefore result in the following. Therefore result in that the graph of capital F is actually the set of points in this form. Where f of t form the input of g, which would be a vector, and then add on to the extra output of f. And what does this graph of f do? The graph of f forms a curve on the surface of the function g. Now, that is something that you might remember we mentioned before. And if you recognize it, hopefully, that would be great. If not, that is the same concept as coordinate curve. The only difference is in coordinate curve, we are drawing a straight line into our domain, and that straight line parallel to the x and the y axis. So this is the exact concept, except that now we generalize to not just having the domain form from a line that parallel to the axis, but now we can actually form a curve inside the domain and then use that to define curve on the surface of the function. So now that concept actually become extremely important later on. So make sure you understand that. All right. And the next topic that I would like to talk to you about, I guess we're probably going to wait for the next video, because I know the last two videos are relatively long. So maybe we'll stop right here for today. And we'll start, pick up the last topic in 6.1 in tomorrow's video. All right. Talk to you guys later. Bye-bye.